So, um, so today we're starting a new chapter and a new section in the text. Um, but before we get into that, let me say a couple things, and then I'll ask you if you have any questions. So first, the exam one test corrections, if you're interested in doing those, are due tonight. Okay, that's a file upload or a text entry. There's a description of that on that item. It is optional; you do not have to do it, but you can get some points back for exam one. Exam two, I have not graded yet, but I'm working on it. Let's see, and exam three, because an incredibly fast-paced course, is next week, normally on Wednesday. I think, yeah. So my plan is to make the test available Monday. Make the test available Wednesday morning, and the latest you could work it would be, let's make it Sunday night. All right. I don't think I've set that in stone. I probably put it in the thing. It's Sunday, maybe Monday. I can't remember where I put it. I wanted to make sure at least part of the weekend was available for you to work that if you wanted. The practice exam for exam 3 is posted as of like an hour ago. Let's see, it covers chapters 7 and 8. So what we're talking about tonight is not on that exam. Yeah. So are there questions about anything?
So you're opening the exam this Wednesday or is it next Wednesday?
It's this Wednesday
Okay.
for chapters 7 and 8.
Okay.
Yep, this Wednesday through the coming weekend. Then, yeah, then next week, and then I think the final's the next Monday. And that my hands are tied. I'll keep it. I'll probably post the final Friday, and it'll be due Monday by midnight. But that's like so far in the future. It's not that far in the future, but it's all material we haven't talked about yet. So cool. Other questions?
Is the final, I'm sorry, I don't know if you just said this. Is it cumulative?
It'll be mostly chapters 10, 11, 12, 13, and 14. But that sounds like a lot. But we will do all of 10 today and all of 11 tomorrow. They're actually pretty short chapters. And then 12 is also thermodynamics, and then 13 and 14 are wave stuff. So it'll be mostly that stuff. So it'll look a lot like what you've already seen. And then there'll probably be maybe 10 multiple choice questions about the entirety. The bulk of the course, though, will be conceptual. So going back through the quizzes from the beginning of the course would be a useful thing.
Okay, thanks.
You bet. Other questions?
For example, like how many questions are you final off of? Like, is it going to be similar to the exams now, and how much time are we going to have if it's longer?
So I may bump up the time from 2 hours. I think in the past it's still been a 2-hour exam, because again, all I'm really adding are 10 more multiple choice questions that are conceptual. So they should be, you shouldn't really need more than 60 seconds extra for each one. So it's an extra like 10 minutes. But I'd be willing to bump up the time. It doesn't cost me anything. So other questions?
Hey, Professor, I had a quick question regarding the 202 course.
Okay.
So currently, I'm not able to enroll in the course just because I haven't completed 201. So what do you recommend that I do?
You could contact the registrar. You should be able to enroll in it, even though you haven't finished this course. I would contact the registrar.
Okay.
Because I would guess others of you have registered. Is anyone else registered for 202?
Yeah, you just contact your advisor and they can unlock it for you.
Okay. Cool. Thank you.
Cool. Anything else? These are good. Going over good stuff. Cool. Okay, so let's talk about chapter 10. So chapter 10 starts the idea of thermal physics, right? So thinking about a different kind of property of matter, specifically related to temperature, right? So temperature and thermal energy. So let's just do this. So temperature is that property that systems, when they're in thermal contact, it's the property that equilibrates, right? So when two objects at different temperatures sit next to each other for a while, again, thermal contact, they come to the same temperature. That's different from thermal energy, right? They may not have the same total thermal energy, but they have the same temperature. And I talked about that in the video that I posted. Let me share this screen with you. The SI unit for temperature is the Kelvin. All right, it's the same step size, the same degree size as Celsius, which means temperature changes in Kelvin and in Celsius are the same. All right. So a delta T, like I say here, a delta T of positive 20 degrees Celsius is the same as 20 Kelvin change. All right, which means when you plug into a delta T in an equation, Celsius is still okay. But if you're plugging in just straight temperature, it needs to be in Kelvin, right? Because Kelvin is absolute. We also talked about thermal expansion. I posted the example for thermal expansion. This is an empirical thing, right? So, so we're just saying when an object increases in temperature, it tends to increase in size as well. And you can think about that in terms of molecular bonds. If you think about an object as being atoms connected by springs, again, is matter really made of atoms connected by springs? Well, no. But the force that connects things, right? The electrostatic forces that go into atomic bonds can be modeled as a linear restoring force for very small displacements. And Hooke's law is a linear restoring force. So mathematically, they actually do act like springs. So drawing atoms connected by springs is not a crazy thing unless you literally think they're little springs. So when you increase the temperature of this thing, basically the atoms are wobbling, right? They wobble back and forth a little bit, and the oscillation of the wobble gets bigger when the temperature gets bigger, and that spaces the entire thing apart, right? So a bigger temperature means a bigger wobble oscillation, and you get an increase in the size of this thing. That also kind of explains why the length shows up in, let me point to that using this. So the delta length, like the increase in length, depends on the initial length, right? So this is L initial, this is delta L, and you're going from here to here, you're increasing the temperature by delta T. You see the same thing with volume, and I alluded to that, but I don't think I want to do that example because it's not super instructive. So let me ask, does that problem make sense to you guys?
Is the change in T, is that temperature?
Yep.
Okay.
Yep. So like example number 1, if you recall from the video, it's you're going from 22 Celsius to 35 Celsius, and so it's a difference, right? It's T final minus T initial. Well, this is a good thing to talk about, actually. So you could say, well, okay, what if I make something colder? What if it's not thermal expansion, but it's thermal like contraction? And I would say delta T has the temperature change, the sign of the, like the direction of the temperature change built into it. So if I was going from, if T initial were 100 degrees Celsius and T final were 80 degrees Celsius, delta T, delta T is T final minus T initial, which is 80 minus 100. That's negative 20, which would mean delta L is alpha L initial times delta T. So if delta T is negative, the length is getting smaller. So whenever there's a delta T, we don't have to think about sign. We just need to be careful about final and initial. Okay. Other questions about this?
Is L initial and delta L, is that the length?
L initial is the initial length, yeah.
Okay.
With the change in the delta T, if it were negative, in the video you said something about it with kinetic, because kinetic can't be negative. Do we have to worry about that?
Well, so delta T can be negative, but T itself, the absolute value, can't be negative. And that actually segues nicely into the next idea, which is, I'll just write it here, guys. So temperature relates to average average kinetic energy of a molecule in a sample. Is this kind of what you were asking about?
Yeah.
Yeah. So so delta T can be negative, and in fact I could have delta K average equals 3/2 KB delta T. So K average can have a delta K average, so K average can change in a negative way, but K average itself can't be negative. So what I'm talking about here, again, this is from the second video, the atomic model of matter. If I have a sample made of, so it's easiest to model this as a gas. Come on. We think of, there's a sample with gas molecules in it, and the molecules are moving at semi-random speeds. So some of them are faster, some of them are slower. But I could define an average, I could define an average kinetic energy, right? If I added up, so I could sum all of their kinetic energies and divide by the total number of things, that would be an average kinetic energy. And it turns out that's related to temperature via this expression. But again, if I had a temperature scale that can be negative, like Celsius or Fahrenheit, that would lead this expression to having negative kinetic energies, and that doesn't make any sense at all. You cannot have negative kinetic energy. So you can use this. No, so that tells us why we need an absolute temperature scale, right? And so, like I said in the first video, the Kelvin scale is absolute temperature, and that correlates to 0 average kinetic energy. Okay. So the other two equations we did for this, let me find the next example. Not that one. This one, right? The other equation we can do with this is if I move this this into the other side, if I move that into the other side, then what I've solved for is the total thermal energy. So E thermal is N times K average, or 3/2 N K T. And that turns out to be a little more useful than K average. So this is the thermal energy of a sample. right? And that's distinct from like the mechanical energy of the sample. So I can ask like, okay, I've got a baseball, right? When you throw a ball, what kind of energy does it have? Well, it's got some kinetic energy, clearly, because it's moving at some speed. So it's got half mv squared. It's got some potential energy because it's above the ground, so that'd be mg like y. But it would also have thermal energy, right? And that thermal energy, now I have a way to talk about that. 3/2 NKT, where N is the number of molecules, T is its temperature, and KB is the Boltzmann constant. And again, that's 1.38 times 10 to the minus 23 joules per Kelvin. And strictly speaking, this equation only works for monatomic gases, but that's good enough for this course. This is not a, we could spend an entire course talking about thermodynamics, and I would wager that you don't want to. So this is good enough for now. But this, including thermal energy, allows us to talk more clearly about conservation of energy, right? So when we said mechanical energy is not always conserved, if I include the thermal energy, then I can think about the actual law of conservation of energy. Okay, let's do an example. Let's go to not that one. Here, example number 5. So how much heat must you pump out of a 10 by 20 by 3 room to reduce its temperature by 1 degree Celsius? It's a very practical question, right? If you're saying like, okay, I need an air conditioner, right, to control the temperature of a room that's this size, right? So I need to know how much energy do I need to pump out, right? So heat is thermal energy. How much energy do I need to pump out to change the temperature by 1 degree? And then you could ask, how fast do I want to do that? And that would inform your choice for like the power of the air conditioner that you choose, right? Okay, so I'm looking for a delta. No, I'm looking for a delta E thermal. How much heat? So let me erase that and just say how much heat. So that's delta E thermal equals. And what do I know? I know a temperature change, and I know a volume. So this is a delta T is 1 degree Celsius. Strictly speaking, that's negative. I really wish I could draw off the edge of the paper. Minus 1 degree Celsius. So if I use -1, then I'm going to get a negative for delta E thermal, which makes sense because I'm removing heat from the system. And then I have a volume, right? The volume is 10 by 20 by 3. What does that work out to be? 600 cubic meters? Come on, Paul. You're working with me, right? And the equation I have, delta E thermal equals 3/2 N KB delta T, right? Like a pseudo-cast version of, it's like a pseudo-differential version of the equation we just wrote. We just threw a delta on the things that are changing. So what I don't know is N. So here, I'm gonna go from volume to N, but how do I do that? I need to know the density of the air, and that would let me do it, right? Because what is density? Density is mass, it's total mass per unit volume. That would give me the, I could use that to find the mass of the total mass of the air. Yeah, total mass. Fine. So say total air mass. And then if I knew the molar mass of the air, I could put these two things together to get N. It's turning out to be a little more complicated than maybe you thought, but it's okay because we were talking about new things. Molar mass is probably something you've seen if you've had a chemistry course or maybe even a biology course. Or if you watched the second video for today's lecture. I did talk about molar mass. Okay, so let me back up a couple steps and kind of talk about this conceptually. So we identified what we're looking for, delta E thermal. We identified what we know. We know total volume, and we know the temperature change that we're trying to achieve. Right, so we wrote down the equation that relates a couple of those things. Notice that what we don't know is number of molecules, right? That's what we need, is number of molecules. But it looks like I can relate volume to mass, and if I know the mass per molecule, then I could put those together and find number of molecules. So that's what I'm going to do. Okay, so we'll find total air mass. Is that what I do? Find total air mass, and then we'll go back and we'll plug into that equation. Okay, so total air mass. Mass equals density times volume. I know the volume. What's the density of air? Well, it turns out to be pretty close to 1 kilogram per cubic meter. That's something you would just look up. I'm going to use 1.2 because that's 1.2 kilograms per cubic meter times 600 cubic meters gets me what, like 700 kilograms. So that's the mass of air in that room. Now I need the molar mass for air. Well, we did this in the video. I can read molar mass directly off the periodic table, but I need to know what the air is made of. What is air made of? Mostly nitrogen, right? So what is the molar mass for nitrogen? Nitrogen, a single atom of nitrogen is a molar mass of 14-ish grams per mole, and nitrogen air comes in pairs, right? It's N2. So that's actually 28. But air isn't all nitrogen. It's also partially oxygen. It's also partially carbon dioxide. I think in the handout I end up using, I'm just using nitrogen. That's fine. It'll get us pretty close. All right. So for the molar mass, I'm going to say 28 grams per mole. Again, so that I'm not losing you guys. I got that number by remembering. Let's just go. I love Googling. Hey, did you know that my my hot tub has a leak in it? Oh, we got a hot tub. Oh man, your life must be great. Well, no, it's not all that great because the hot tub has a leak. I need a periodic table. Had this hot tub since we moved into this house. Never used it. I thought, okay, kids are old enough. Come on, Google, you can do this. Just want to flash a periodic table so I can show you. That nitrogen has a molar mass of 14. Give you 5 more seconds. Okay, so imagine that I brought up a periodic table and did not mention my hot tub, or the big puddle in the yard. Again, you can look up the molar mass for nitrogen. It's 14 grams per mole, and nitrogen gas is N2. Okay, so now I can put these two things together. Let's use a different color, sure. This is the total mass. This is the molar mass. I can put those together to get mass, nope, number of moles, right? So here, so this number of moles is total mass divided by molar mass. All right, and I'm gonna have to be careful with the units because I've got 720 kilograms divided by 28 grams per mole. But one of those is grams, the other is kilograms. So I need one of them to be in grams, or the other to be in kilograms. Let's convert molar mass to kilograms. So to convert molar mass to kilograms, like that sound effect, I'm just going to multiply by 10 to the minus 3. So 28 times 10 to the minus 3 kilograms per mole. So that's 0.028 kilograms per mole. That's going to give me number of moles. Fabulous. Turns out to be 25,714. 700 moles. Great. Are we there? Not hard. We're close. We're close. So maybe I shouldn't put a just a double underline. So now I have number of moles, right? And what I'd like to do is plug that in. Come on, man. Same team. Here. But capital N is number of molecules. So I can either convert from number of moles to number of molecules, or I can remember that anytime I have, come on, N times a Boltzmann constant. Oh, we're doing all sorts of things today, you guys. N times the Boltzmann constant is the same as lowercase n times the gas constant. All right, and again, I talked about that in the pre-lecture video. So I can also rewrite this. I don't think I talked about it for this though. I talked about it for the ideal gas law. So I can rewrite this as 3/2 in R delta T. But how do I know when to use which? They're both true. If I have number of things in molecules, I'll use the in R version. If I have a thing in just straight number of things, I'll use the in K version. All right, but they're both true. Okay, so we are there. We can just plug in now. 3/2. Number of moles was 25,714 moles times the gas constant is 8.314. Notice that's 8 and then pi, right? That's how we remember that. You don't have to memorize that, but I did. Okay, so 8.314 the units on that are joules per mole Kelvin times the delta T is 1, -1. And it's a delta T, so degrees Celsius and Kelvin are the same. I'll put Kelvin there just so that it cancels with the Kelvin. Okay, so a quick jog to the calculator, and we get 320,683 joules, or about 320 kilojoules, which seems like the scale of energy we should have to pump out of a room to change its temperature by a degree. Questions about this so far?
Yeah, can you explain when again how when you're supposed to use big N and when you're supposed to use, or like big N times the KB or the lowercase n times R?
Yeah, so if I could rewrite, in fact, we'll see this in the around that time. Here, so I could rewrite E thermal is 3/2 in KT, but it's also 3/2 in RT. So honestly, I can get E thermal from either one of those. So I generally just use whichever one jives with what I have from the problem. So if the problem tells me a number in moles, I'll just use the R version. If the problem tells me a number in like straight number of things, I'll just use the in KB version. Does that make sense?
Yeah.
We see the R version often in chemistry. That's just the version that is convenient for that field, because lab scale number of things tends to be single moles to like fractions of moles. Here we see, the number of air molecules in a room is tens of thousands of moles. But all of those numbers are ridiculous when you talk about straight number of things, like 10 to the 26 of those, 10 to the 20 to 10 to the 26. They're all absurdly large. Okay, so let's do the next bit here. The next bit is, what is a typical speed of an air molecule in the room? Let's assume we're at room temperature. So a typical speed. So I'm looking for a V. But I already alluded to the fact that all of the molecules in the and the gas here are moving at kind of random speeds. There is a distribution to it. Actually, if you take more thermodynamics, you will talk about and maybe even derive the Maxwell-Boltzmann distribution, which looks kind of like this. Kind of. This is velocity. It's actually more. It's more like over here. Has a tail like this. This is velocity. I want that V to not look crazy there. And the fraction or number, or let's just say number. Right, so that's, again, what we call the Maxwell-Boltzmann distribution. I'm not going to derive that in this course. We're not even going to talk about it past this. But you can define a couple things. You can define like the peak. You can define an average, which turns out to be a little higher than that. And you can talk about what we're going to talk about, which is the RMS velocity. Okay, so one way to get a typical speed. Again, typical speed is not very descriptive. It doesn't say like which one of those. You could do an average, you could do a most likely. But what we're going to do is this. Remember we had K average equals 3/2 kBt. We could also call that half mv squared. But it's not the average because we're squaring when we do this. So this is some I'm gonna label it what it is. Some special speed here. So if we math this out, if we solve this for VRMS, I multiply by the 2, that goes away. I can divide by an m, and then I'm gonna square root. So what I have is the square root of 3 kb t over m. But you could also write this as the square root of 3 RT over the molar mass. So I'm not going to talk about, there's a more like theoretically sound way to derive this, but I'm not going to do it in 6 minutes. So what is this RMS? What does that mean? RMS is root mean squared. What we've really done is we squared the velocities and took an average of the square velocity and then square rooted it, right? Because what is kinetic energy? Well, it's proportional to V squared. So we took an average kinetic energy, which is proportional to V squared. So it's the average V square, right? So we're basically saying average V square. Come on. Here I am deriving it. Here, the app, my hand. It's just that part of my hand doesn't like me. So we're square rooting the average V squared. That's basically what this is. Okay, and if all you get out of that is, I don't know, there's some special velocity that's called VRMS, that's fine. Okay, so RMS velocity is something we can calculate. Let me say one more thing about it. It's not the average velocity, it's the velocity of a molecule with the average kinetic energy. All right, I'll say that one more time. It's not the average velocity, distinct from an average velocity. It's the velocity of the particle with the average kinetic energy. Okay, so I can just plug into that to get a typical speed. What am I going to do? We'll plug into this one. So 3 times 8.314 joules per mole Kelvin times the temperature. And this time, the temperature does have to be in Kelvin because it's not a delta T anymore, right? So I'm going to move this down so I get a little more space. 3 times 8.314 times, what is that? 20 plus 273.15. That gets that in Kelvin. divided by the molar mass, which was 28 grams per mole. But again, to get this in SI units, that's going to be kilograms per mole. So I'll multiply by 10 to the minus 3 kilograms per mole to the 1/2. And if you do that math, you get probably something like 300. Here's my mouse. 500. 511 meters per second. Okay, let me pause. What questions do you have about that? So we defined, we did an example with thermal energy. It's useful to know because we're modeling this gas as like molecules that are moving around. So we can ask, how fast are they moving, right? Are they meters per second? Are they tens of meters per second? Well, it turns out they're hundreds of meters per second, right? Which is why I ask, what is the momentum of an air molecule? I'm not going to do the math, but it's just very small, right? Because what's the mass of a single nitrogen molecule? It's tiny, right? We said that the atomic mass unit is like 1.7 times 10 to the minus 27 kilograms. So we've got 1.7 times like 28 times this velocity to get momentum. It's still really, really small. I compare that. You can look at it in the handout. So hundreds of meters per second is not a crazy speed for gas molecules to be going at room temperature. So let me talk, I've got about 60 seconds left. Let me talk about this last idea, and I'm just going to use this for blank space. I just want some blank space here. So the only other thing I talked about, and if you've had a chemistry or physics course before, you may have seen the ideal gas law. The ideal gas law relates pressure, volume, number of things, and temperature for a gas. For an ideal gas. So we're treating the gas molecules like solids, treating them like they don't interact with each other. And we're treating it like there are lots and lots of, it's very big. So basically, if you have, so there are 4 things here, right? Plus a constant. If you have 3 of those, you can calculate the 4th, right? And if you change one of those, you can see how the others change. And I talked about this for a sealed container. N is constant. Say N/N is constant. That's supposed to be the letters CONST, constant. So then you can say PV over T is a constant. So you could say, well, if I change those, I can relate it to another set of these. And my argument here is that it's not super clear if you say, let's say I know a pressure, volume, and temperature, and I change the temperature. How does the pressure change? And the answer is, well, it depends on how the volume changes, right? If the volume doesn't change, then you could rewrite this as P1 over T1 equals P2 over T2. And if you've had a chemistry course in particular, you may have seen versions that are like this. Or if the temperature doesn't change, it's P1, V1 equals P2, V2. These have names, right? One of them is like Charles' law, and the other is Boyle's law. I don't remember which is which and whose is whose. Because all I really remember is the ideal gas law. But these 2 equations were noticed before we had the ideal gas law. Okay, so let me say one other thing, and maybe we'll call it good. We can also rewrite this instead of in K, right? I said anytime you have in K, you could write it as in R, and you can write this as well. All right, so the ideal gas law shows up in either way. And again, same kind of logic. you use the version that makes sense for the problem you're working. So unless there are any questions, I'm going to call that good. I know I didn't do an example with the ideal gas law, but you can see an example like that on the handout. And we'll be working with the ideal gas law in the next 2 chapters anyway. So you'll see a lot of this in the next 2 or 3 days. So are there any questions? Okay, then I thank you for your attention. Have a great evening. And I will see you guys tomorrow.
See you, Professor.
Yeah.